Welcome for this week 10 session, live session for Smart Grid Basic to Advanced Technologies. We will start with the overview of week 10. Tomorrow is the deadline for submitting assignment 10, and for assignment 11 the deadline is October 11. This recording you can find on this page. Did you try to access the recordings? Are you able to access these recordings?
Yes, sir.
Let us begin with the week 10 overview. So, just as I told you in the last session also, that these last 4 weeks, 8, 9, 10, 11, 12 material, it's 9 to 12, they are all demonstrations. So whatever we have covered till week 8, their demonstration is covered in the subsequent 4 weeks. So in the last week, we saw a demonstration of solar generation, wind generation, and then battery, cell balancing, passive and active cell balancing. So all these things, and today we will see this demonstration of AC microgrid, DC microgrid, and AC-DC microgrid, hybrid microgrid. So theoretical aspect we have already covered in previous weeks. We will see how we can actually do it, implement in a laboratory setting. And then demonstration of parallel inverter operation in AC microgrid. Finally, this last topic was covering the harmonic effects and their mitigation techniques. So we'll see them one by one. Before starting with the demonstration, so whatever demonstration we do, first of all, why do we need to carry out the simulation? Can you tell why do we need to go for simulation and testing before actual implementation?
To study the system, simulation is required first. Then only we can implement in real time.
Yes, it is correct. We have to, suppose we are trying to implement any protection strategy or a new inverter we want to install a new solar or wind farm, or we want to create an entire AC or DC microgrid or hybrid AC-DC microgrid and integrate it to the existing system. So before actually doing that, we need to know what will be the challenges while integrating, and because already the system in place is working very fine. If we, without any testing or simulation, if we directly install anything, then and if it creates trouble, then it will be very difficult. So beforehand, we try to see what all challenges will be there while integrating. So for that, we need to create a model of whatever we want to integrate into the system. Suppose we want to integrate a DC microgrid into the existing AC microgrid, or even if it is isolated also, then different components which will be connected within the DC microgrid, they will be integrated to a common DC bus. So how are they going to behave when they will work together? That we have to study first. For that, we model all the components which will be present in the system using some software, and then perform different kind of studies. And these simulations also help us to do, in the actual system we don't know what will happen when the contingencies are there, and we cannot create contingencies in actual system, but we can do that in simulation platform. We can create several cases, several kind of contingency. We can remove one line, we can increase the load, we can reduce the generation. We can do anything in simulation and see what is happening, how much time the system is taking to restore the supply if fault is there, how much time it is taking to restore the voltage to its nominal value. So all these things we can do in simulation, so that when we install the actual system, our system should be robust to all kind of contingencies, all kind of adversities. So for that we have to do so many studies, so that several possible cases can be simulated beforehand, and the system is working fine for all the cases, and we can make sure that it will actually work in the while real implementation also. So first we do simulation. The simulation is done in a software itself. We have these now real-time softwares which are based on EMTP, the electromagnetic transients. So they will model everything using these electromagnetic transients, the electromagnetic theory that we have studied. So all the models are based upon that. So because those models, they work at very small time steps. They can work at microseconds level also, millisecond, microsecond levels. Whatever changes we do within the simulation, suppose I increase the load, so I can see the impact within few milliseconds itself. So these simulators are very fast, very quick. So one example is this RTDS. So these are very fast simulators. So these are much faster than the offline programs. So MATLAB is an offline program, so it takes time. If you would have done some simulation on MATLAB, and Simulink is platform for simulations in MATLAB. Simulink takes a lot of time, especially when we want to study the entire dynamics of the system. Then it takes a lot of time because it has to solve these differential equations. It takes a lot of time. So it's an offline program, but RTDS, these are very fast programs. So mimicking almost in real time the actual system. So that is why they operate in real time, mimicking the real microgrid system, and they can respond in real time to any modifications in the parameters. So first of all we do the simulation, then we do testing also. Now in testing, simulation is done only in the software, at software level, but we want to also check how the integration of hardware will impact, because that is, software is just equations, mathematical model, but actual hardware may have non-linearities. There are several additional things that also we need to take into account. So for that we have this hardware in loop testing system. So we have, suppose we want to install a big wind farm, 5 megawatt, but we can have a small solar panel mimicking that. We can have a small battery also. We can have a small EV charger also. So we can scale down that system to a smaller level. In per unit we can have same. So if we convert them, bring in on a per unit level, we can see what are the impacts, what are the changes happening because of different contingencies. So we can have these small equipments connected in a loop. So that is why here it is hardware in loop. We connect actual hardwares, not just software. So we can have small PV, solar PV, a wind turbine also, a small DFIG. We can have a storage, lithium-ion energy storage. We can have fuel cells, and we can have supercapacitors. So here in hardware in loop test, we will use them as actual hardware. We will have small PV systems, small fuel cells, small supercapacitor of small ratings, not the one which are actually used in the system, because that will be very big. And here we will be having only mathematical models for all these. In simulation we have only mathematical models, but here we can have real hardware. And our actual network, we may not be able to integrate that in actual network because before installation we want to test. So that network will be inside RTDS. That will still be a mathematical model. Network is still a mathematical model, but these different entities, they can be actual hardware of smaller ratings. So is this clear? The difference between simulation and testing? So after doing both simulation and testing, or we can even, so after simulation and testing, we will do the actual installation. Now testing can also involve these, or even after installation also we can see the performance of the system using these digital twins which we have discussed earlier also. The post installation also we can monitor the performance and even improve it using these digital twins. So is this clear? Let's move ahead. So the first was the AC microgrid case study. So as we have already seen in any type of microgrid, we can have these. So we have seen this three types of microgrid: AC microgrid, DC microgrid, and AC/DC hybrid microgrid. AC microgrid we can have easily because we actually have these existing system is AC. So installing AC microgrid will not be a challenge. But from AC we went to DC because of we have these sources, several loads are DC, several sources are DC, so we want to avoid these intermittent in between these conversion stages, AC DC, DC AC, DC AC DC. So then that is why we went for DC, but actual system is still AC. So the most practical, we cannot have completely DC microgrid. The most practical thing is to have a hybrid AC/DC microgrid. So we can have DC also and DC. So that is why I will be studying. All these three case studies will be there. So DC, where can we find DC microgrid application? Although we cannot have a fully DC microgrid, but where can we use DC microgrid? So we can have an isolated DC microgrid for remote areas, right? There if we have solar PV, we can have wind, we have energy storage loads, so we can connect them to a DC microgrid. So let us, first is the AC microgrid. In each of these microgrids we can have three modes. One is grid connected mode, then we have islanded or isolated mode, and then we have transition mode. Here we'll be considering these two modes, grid connected and islanded or isolated. So here in this case study we have one storage, one diesel generator, AC load and solar PV. Why do we need diesel generator here? Can you tell? Will it be required?
For sir, reactive support, sir. Reactive power support and active power support if needed.
Yeah. So when will that active power needed? Yeah, black.
In isolated mode, it may be needed, sir, if PV is not working.
Correct.
Yes.
So in evening hours when PV is not there, because it will be there only up to 5 p.m. let's say. Maybe maximum up to 7 p.m. So that too with the reduced intensity. So beyond 7 p.m. it will not be available. Solar will not be available. So then if battery is also, the SOC of battery is also less, then we'll have to use the diesel generator. Especially for isolated grid, we'll be requiring this diesel generators. So in grid connected mode, grid will be supplying the load when there is no PV. Because grid is connected and we have to supply the load. If PV is not there, then grid will supply. And PV will always operate at MPPT. This we have discussed before. Why PV should always operate at MPPT? Yeah?
Because grid is there, sir.
Grid is there, will happen. What is the benefit of operating at MPPT?
Maximum, it can give maximum, and we can charge the batteries.
So, because it is connected to grid, whatever PV is generating can be utilized. So we can extract the maximum output from PV and either charge the battery, or if battery is fully charged, we can supply it to the grid. So that is one advantage. So energy storage can charge as well as discharge based upon the reference signal. Because if it is already fully charged, then it cannot charge further. And it can discharge to provide certain kind of services. And the diesel generator will help in voltage regulation by excitation control. So diesel generator has two types of inherent control which we have in the other conventional synchronous generators also. That one is speed governor control for controlling the speed by varying the input mechanical power, the steam or here diesel. Then we have excitation system to regulate the voltage by varying the field current to regulate voltage. So here in grid connected mode, it will help in voltage regulation by controlling its excitation. When the microgrid is isolated mode, then PV may or may not operate in MPPT, because if storage is already fully charged, then it will not operate in MPPT. If it is not charged, then we want to extract maximum from the solar PV and charge the battery. But if it is already charged, then no need. Then we can use it for voltage and frequency. Then energy storage can charge and discharge based on reference signal, and diesel generator in isochronous mode and provide the voltage and frequency control. So why it is isochronous? tell? Because you want to control the frequency. You want to maintain the same frequency.
No need of synchronization.
Due to synchronization,
Yes,
here the grid is not there, no? Isolated.
yes. Then DG can operate for independently.
Yes, so as we have already discussed in previous week that these converters are grid following converters. So here DG will provide that voltage and frequency. That is why DG is here providing the voltage and frequency control. So it has to maintain voltage by excitation control and frequency by the governor control. So it will maintain voltage and frequency because here grid is not present. So voltage and frequency references are not available from the grid side. So the diesel generator has to provide that voltage and frequency reference which the PV will follow. So same thing here again. The voltage in grid connected mode in off-peak hours. So these were the different cases which were discussed in the simulation study. So in grid connected mode there were four cases, and isolated mode there were three cases. So I have just classified them. Because first two were simply without the DERs. No DERs were there, only grid was present and load was being served. So that was simple. Entire load will be served by the grid itself. In first case, there was no DER, only grid was supplying the entire load. In second case, again grid was supplying the entire load, only the grid was increased from 0.5 to 1 per unit. Increased load. Then there were the rest two cases which were off-peak hour and peak hour. So in off-peak hours mean we have the load is less. So in this case, because off-peak hour load is less, generation is still there, the battery can charge. PV will operate at MPPT to charge the battery, and diesel generator will help in voltage regulation. And in peak hour, what will happen? Load is more. Then the solar generation. So in this case, what will happen? The energy storage has to discharge because PV is less. So it is reduced. PV is reduced, but operating at MPPT. So whatever reduced power is available, we want to extract it maximum. And diesel generator is still operating in voltage regulation. So here it is grid connected, right? In first two cases, the grid was supplying the load. Again here also it is grid connected. So why are we not taking power from the grid? Although it is grid connected. Can you tell? So all these four cases are grid connected.
Power will be costly, sir, in peak hours.
Costly, why costly? Yeah, it can be. It can happen if we are taking power from real time market. That is correct. One That is a good observation. And any other reason?
81 किलोमीटर ऐसा वो सबसे लंबा है और उसके बाद थोड़ा छोटा है 84.5 ऐसा कुछ है
That is correct. If real time market prices are high, then it's better to utilize our local generation. Rest we have seen before also. What are the benefits of using microgrid? What we want to reduce losses. We want to reduce losses. So if local generation is there, then losses will reduce because the power need not travel longer distances through the transmission system than to the distribution system. Because we are already generating locally, we need not import power from the grid side. So we can reduce the transmission losses in that case. Then we can reduce reliance. On power from the grid side. In that case, we can have high reliability. Reliability will improve in that case. There is some fault on grid side. We can still operate in isolated mode. Even in grid connected mode. We want to minimize the dependence on the grid. We have battery, we can charge it during off-peak hour and discharge during the peak hours. So we can reduce the transmission congestion. So transmission congestion can reduce. So these are several different advantages of using microgrid. So that is why here in grid connected mode also we are trying to locally whatever is available with us we want to first use that and then use whatever is required. If it is not being met locally, then we can import it from grid. The next case is the isolated mode. So in this case, energy storage can charge. If first case where energy storage is charging. So in this case, isolated mode, there is no grid, so voltage and frequency reference has to be provided by the diesel generator. So that is why diesel generator in voltage and frequency regulating mode. So there can be two cases. One is energy storage is charging, PV operating at MPTEL. Second is where PV generation is less, reduced. So we can say off peak, evening hours we can say. Close to evening hours where the PV generation is less or even the morning hours. So in that case, because we have to meet the load, then ES will discharge, energy storage will discharge. So is this clear?
Yes, sir.
Okay. This is, next one was the demonstration of the DC microgrid. In this also two cases were considered. First was where there is only one microgrid, one DC microgrid. Second one was where there were two DC microgrid, two standalone DC microgrid interacting with each other. So what we have seen the benefits of having two microgrids, DC microgrid connected with each other. So what are the benefits? Can you tell some benefits? When two microgrids are interconnected, DC microgrid, what benefits can we derive?
Reliability will increase.
Yes, correct. Reliability will increase because if we have suppose excess generation in one of the distributed in one of the microgrid and lack of generation in the other, then this first microgrid can supply the load of the second microgrid. That is correct. So we can have also we can have better utilization of these resources, renewable energy resources in both the microgrids. So we can operate the RE in MPPT mode most of the time because even though load maybe less in one microgrid, it is still there. We can supply. So we can have better utilization of resources, good reliability, lesser cost. All these are advantages. Starting with standalone microgrid. So here in this case study, so this because this is a DC microgrid, there is only one DC bus. And all the loads and generation are connected to this DC bus. Because solar PV is already a DC, but we need a DC-DC converter, DC-DC boost converter. So why do we need this DC-DC converter here? Solar is already DC. Why not directly connected to DC bus? What is the advantage of having DC boost converter? Can you tell?
To meet its bus voltage level,
Can you repeat?
to meet with the bus voltage level means DC bus voltage level.
Yes, correct. One is to we want to regulate we want to have a constant DC bus voltage. EV voltage is fluctuating. That is correct. And second, one more, any other utility. Why do we need?
To provide reactive power also.
Well, this is DC grid, so there is no reactive power.
Sorry, I have not seen that.
So one important thing which we were talking recently for MPPT also we require, right? For extracting maximum power from PV, we need one control. So that we in the previous session we discussed here we have PV, solar PV. Here we have some load. So when will maximum power be transferred from solar to load? So let's say solar.
To announce the source impedance and load impedance.
Yes. So let's say load impedance is RL, and the effective impedance seen at the terminals of solar PV is our let's say RPV. So we want to match these two resistances or two impedances. So who will do that? So the DC-DC converter will help us. So it will help in two ways. So one thing here it will maintain a constant voltage. It will try to maintain a constant voltage here. Regulate this voltage, and then it will also vary this voltage. So that these two impedances become equal to extract the maximum. So for these two, we require the boost. So this voltage may be less than the DC bus voltage. So we want to boost the voltage.
Power will only flow to the DC bus if the voltage is more. So that is why this DC-DC conversion is also required.
Mm-hmm. So these are the requirements for using this conversion here. Although it is DC. Then we have diesel because it is AC, generating AC current. So we need AC to DC converter here. Then battery is already DC, still same. And here, what about battery and supercapacitor? What kind of these converters do we need here, and why?
Bidirectional because they have to charge and discharge.
Correct. So these two are bidirectional current. bidirectional converter. Absolutely correct, because they have charge as well as discharge. So these are DC-DC bidirectional converters. Then we have wind also here, and wind is AC. Then so we need AC-DC and DC to AC here. Here also we have this MPPT. We have to implement MPPT here. And it's a variable speed drive. So we need this back-to-back converters. So, and loads are already DC. So here,
No. With this wind side, there is no MPPT. Wind side, there is no.
inside also MPPT is there.
Okay.
We can
as
have
per as per the wind characteristics.
yes, correct. So
The
just
pitch and all, pitch will be regulated.
correct. So just as we have solar PV characteristics, so we want to operate at this point. Similarly, we have wind characteristics also for different wind speeds, and we always want to operate at this maximum point, irrespective of the wind speed. Even if the wind speed is reduced, we will change this beta such that using that pitch control such that we track this. We operate at this point. So both solar and wind have these MPPT algorithms. So this is the algorithm which is used here. So we'll see this algorithm. It is based upon the available generation and storage. Thus, the state of charge of storage that we have. So we have to see there are first initially starting with two cases. There are two possibilities. Either generation is less or more than the load. So first case is generation is excess. So in that case, what can we do? If generation is more than load is already been supplied. What can we do with the excess generation? So what should we do with the excess generation?
Charging batteries.
So we can charge the battery, because when the generation will be low, we will need that. We need to supply the load. So that only storage will be doing. Because this is a standalone microgrid. Grid is not there. So we need the the generation when renewables are producing load. So first case is this, when the generation is so EG greater than PL. That means is generation greater than load? Yes. If it is so, then there is another condition on battery. If state of charge is already more than 90, we cannot charge the battery. So in that case, battery will not be charged, and PV and wind will regulate the bus voltage. But if storage SOC is less than 90%, we can charge. PV and wind will operate in MPP. So here both will operate in maximum or power mode. So this is first case when the generation is more than the load. This is easy, straightforward. But when generation is less than load, then there are several cases. So first thing, if generation is less than load, we have to see the battery, our storage. So is storage SOC less than 40%? If no, that means storage has more than 40% of charge. Then battery can discharge. And PV and wind are still operating in maximum power. So whatever reduced power they are generating, we want to still extract the maximum power from that. But that power is less than the actual load requirement, so the battery will provide the remaining power. So this is also done. Now remaining cases are here. Here we have several cases. There we will also use the diesel generator. So we are using diesel generator as the last resort, because we want to, first of all, diesel generator is costly. Second, it is emitting, thermal emissions are there, carbon emissions are there. So we want to reduce these. So we want to use diesel generator only when the storage is not sufficient and generation. So if storage SOC is less than 40%, then we have to check the diesel generator. And what we have to check? We have to check whether the power of PDG, the output of DG is greater than P load minus P generation. That is load minus solar plus wind generation. That is if load is more. If load is more than, if diesel generation, the output of diesel generator is more than this difference, P load minus P generation, then diesel generator will provide that and battery will be charging. Okay. So here diesel generator will supply the load as well as charge the battery. If the output of diesel generator is less than the PL minus PG, so diesel generator cannot do anything here because its output is less, then battery will come into picture. So for both the cases, either diesel generator is not available, in that case also storage will provide, and if diesel generator output is less than the actual requirement, then also storage will do. So both A and D cases will be handled by the storage. So here we have to see, because these three loads, here one load is critical load and these two load are non-critical loads. So two are non-critical loads, I think. Yes, two are non-critical loads. So based upon the storage SOC, load will be curtailed. If the SOC is more, all the loads can be met. As the SOC goes down, we have to curtail one load, starting with the non-critical load. So here you can see SOC is less than 40%. No. If SOC is more than 40%, battery will discharge and all the loads will be supplied. If it is less than 40% and more than 30%, so between 30 and 40%, one critical load will be curtailed. And if it is less than 30%, then only critical load will be supplied. This is when the diesel generator is not available. So in D case, when diesel generator output is less than PL minus PG, then this will happen. Here SOC is less than 30%, all the generators, all the load will be supplied. And similarly, when SOC reduces, one non-critical load will be curtailed. So is this clear?
Yes, sir.
Yes, but who will check this SOC level?
All these things will be done automatically. It is inside the control of this control, because this microgrid will be having a controller, right? So that will be checking, always doing this check. So SOC of the battery will be checked, and it will always be compared. So this algorithm is inside the controller that will be doing it. So it is automatic, not manual. We don't have to give any instruction. It will be done automatically. As soon as the SOC goes below 30%, load will be curtailed automatically, because we have a relay here, right? You can see here we have relays. So as soon as the controller knows that the SOC is below 30%, this relay 3 will be opened. So load 3 will be curtailed. Okay.
But then why DG set is not feeding at that time?
Because diesel generator output is less than load minus generation.
Oh,
Like requirement of
okay.
load is. So if it is more than that, then the gap will be supplied by diesel generator and it will also charge the battery. So that PL minus PG will be supplied by DG and excess will be used to charge the battery. But if it is less than that difference, then it cannot do. It cannot supply the load. Okay. This is the next. So this was the first one was isolated single DC microgrid. Second one is when there is isolation, means two DC microgrids are isolated and both are interconnected. They are connected using this dual active bridge, which provides the first is this first microgrid and DG microgrid 2 second. So both are autonomous microgrids, and the one advantage for this interconnection is these two microgrids need not operate on same voltage level. They can have different voltage level as in that case study. This first one was operating at 380 volts, I think, 380, and yes, 380 and 48 volts. So this is a low voltage DC microgrid, and so load requirement will be also be lesser here, maybe I think 200 watts per there. And here the load requirement will be more because voltage levels are higher. The two independent DC microgrid operating at different voltage levels can be interconnected. As we have seen, we have advantages, several advantages can be obtained by these interconnections. So we can have reduction in cost, high reliability, supply quality, improvement, local energy security, and interconnection at different voltage levels. So these are the advantages. So reliability will increase and better utilization of resources, utilization of renewable resources is also possible here. So how reduction in cost? Because diesel generator, if we have diesel generator, because both are autonomous microgrid, and if there was no interconnection, as we have seen in the previous case, we had to use the power from the diesel generator, which is costly. But here, because we have an interconnection, if we require that power, we can have it from the another microgrid. That is still from a PV source. That is cheaper than the diesel generator. So there is a reduction in cost in that case. Why are we using this? Another advantage of using this dual active bridge converter. See here, both side we have H bridge converter. So this entire setup is called this dual active bridge converter. In between this side we have DC, this side also we have DC. In between we have a AC interface. So which is having, this is it's a high frequency transformer. Why are we using this high frequency transformer? Because this dual active bridge has certain advantages. First, it provides a galvanic isolation because of this transformer. Because transformer, we see primary and secondary side, they are not electrically connected. If we have this, take this single phase transformer, this is a magnetic core. Here we have primary winding, here we have secondary winding. So these two are not electrically connected. Electrically they are not connected, but they are connected magnetically, they are coupled. So they have a common flux. So if there is a fault this side, it will not be propagated on this side because electrically they are not connected.
But these are two DC, na? DC means transformer is the AC component.
Yeah, but although this side it is DC, but output of this active bridge is AC, because what this bridge is doing, it is converting DC into AC. This is also converting DC into AC. So in between we have a AC interface. So on both sides of the transformer we have AC only. Here we have DC. This is DC. This is also DC. So this bridge will convert this DC into AC. This is at 48 volts. And this is at 380 volts. This will also be converted into AC. So both sides we have AC and we have a transformer here. So is this clear now?
Yes.
So because of this is the good advantage. Because of this we have a galvanic isolation. And also another advantage is that bidirectional power flow is possible with high power feeding capability. And large conversion ratios are also possible with dual active bridge. With simple buck boost converter, conversion ratios are they are limited to non-isolated type of converters, which are buck boost and buck boost. They only provide a conversion ratio of 1:4 only, maximum 4. If it is boost 1:4, buck then 4:1. But these isolated type of converters, they can provide more than that. So we can have this higher. So here you see 48 and 380 conversion ratio is almost 10 times. We cannot use these non-isolated converters, DC-DC converters, and also they will not provide that isolation also. So these are several advantages. And also we need bidirectional power flow. If suppose generation is the simple non-isolated buck boost, they are not bidirectional, but we can make them bidirectional, but still they will have isolation is not there. Here, why do we need bidirectional, or why this dual active bridge converter has to bidirectional? This we have discussed. Can you tell?
Because of the power flow from one grid to another grid, load sharing.
Yes, correct. So there can be cases when generation is more here and load is less here, generation, and vice versa. So generation can be more on either of the side. So they can share in between them. Both side power flow can be possible. So that goal is to supply the entire load. So we can take power from any of the sides. So this was for DC microgrid. Then the next was for AC/DC hybrid microgrid. So now in DC we do not have reactive power, right? But AC/DC we have to think about this voltage regulation because AC is there. So V and Q both will come into picture here. That is why. So before starting that CVC is coordinated voltage control, and its objective is to utilize all the available voltage regulating devices to increase the overall reactive power reserve, to keep the voltage within the nominal limits, and also reduce the post-fault voltage recovery time. Because during fault voltage dips, right? Because current will increase. Current will increase to a very high level and voltage will reduce. Whether it is any kind of fault, LG, double LG, triple LG or LL, voltage will reduce. So if reactive power support is more, then voltage can quickly build up. So if good amount of reactive power reserve is there, post-fault voltage recovery time will be reduced. And that is to be ensured by all these available compensating devices, voltage regulating devices. So this CVC can be centralized as well as decentralized. So centralized will require communication. And this will not require communication. This is decentralized. Each one of them will be having their own voltage regulation. Here we have seen three types of control, right? Centralized, decentralized, and third one was distributed, which has advantage of both of them. So here we have a problem of single point failure, and that is overcome here because of peer-to-peer sharing, information sharing, or communication, you can say. And here there is no communication at all. So single point failure, no communication. So both are overcome here. So it is having peer-to-peer information sharing. So first of all, that decentralized one was discussed, and then one approach was given without any communication. Also, they were able to maintain the voltage within the limits using distributed controls. This was one diagram for voltage and Q requirement. So there are three cases or three state, we can say. Three states. One is steady state, then second is dynamic state, and third is transient state. This dynamic is very sudden changes. So here we need a sudden load switching is there. So in all the three cases, voltage and Q limits are there. So first one, steady state, Q requirement is very less in, because steady state is steady state, so the disturbances are very small, very less. Load switching means load generation imbalance is very less. So here Q requirement is very less. It is less than 40%. It is much less than 40%. So from this state we can move to any of these state depending upon the voltage level in the system and the Q requirement. In second state, which is the dynamic state, Q requirement is 40%. Hard limit means we have enforced that Q requirement is 40%, exactly 40%. And then third is entire Q limit up to 100%. So full Q requirement is there. So that is especially for fault, because during fault the voltage suddenly dips to a very small value. It may even become close to zero. At that time we have to very fast, because voltage level is reduced to such a small value, Q requirement will be very large. So 100% Q which is there should be present for this fault, for this transient state. So one can move from one to second, any other state, depending upon what the voltage is and what the Q is. So if from dynamic to steady state, in steady state voltage is within the nominal range. That is nominal range. What is the nominal range of voltage? Which is, if you consider this, what is the minimum voltage here?
0.9 to 1.1 pu.
Yes. So here it's 0.9, minimum voltage is 0.9 and maximum 1.1. So especially it is in transmission system. Generally even it may be less than that, maybe even 0.5 to 1.95 to 1.05. Okay, so if voltage is more than 0.9, that is, it is already in the steady. If voltage becomes more than 0.9, it will enter the steady state, and the Q requirement at that time will be less than 40%. If the system is already operating in state 1 and the voltage is still more than 90%, but Q requirement is more than 40%, then it comes to dynamic state. From dynamic state to transient state, if voltage becomes less than 0.9, then it will directly go to the transient state. At that time, once it enters the transient state, full Q requirement is there, 100% Q is required. From transient state, if voltage, because here in transient state voltage is less than 0.9 per unit. If now voltage becomes more than 90% and Q requirement is 40%, then one goes to dynamic. And if Q requirement is less than 40%, then it goes to steady state. So in either state 1 or state 2, if in any of these two states, if voltage becomes less than 0.9%, directly it will go to the transient state. So these brown arrows show that transition. In both the brown arrows, we can see as soon as the voltage goes below 0.9, it enters the transient state. Whether earlier it was in steady state or the dynamic state. We can see this one and this one. And then again it can restore the previous state based upon the Q requirement. Okay. So this was a difference. This was a proposed scheme in the case study, and these are the existing schemes. What existing schemes are doing? If all these different voltage regulating devices if they are operating in decentralized mode, that means suppose just as in that case study example was given for IEEE 33 bus system. So we have different buses, and let's say these different devices are present at different buses. I think these are the buses. So if three devices are present as three different buses, each of them will be working only on their respective buses, voltage at their respective buses. Suppose this V5, V1 and V22. So the voltage regulating devices available at these three buses will be regulating the voltage at their respective buses only. They don't know anything about the voltage at the other buses because they are not communicating with each other because it's a decentralized control. So they are not aware about the global voltage requirement, voltage limit requirement. So they give importance to speed of. The first one is this. So they do not check for availability of devices for operating conditions. Second is this, they give importance to speed of operation of device only. And all the fast acting devices are considered for Q along with slow devices. So out of the available devices for voltage regulation, some are very fast. They can operate within milliseconds and some may not be able to do that. Let's say OLTC. OLTC is a mechanical device. So there are taps on the transformer, online tap changing transformers. The taps are mechanical. Mechanical systems are always slow as compared to the other converters. So they are slower. And if all of them are considered together, then the fast one will do it work and slow has not even started. So that is the problem. If they all of them work together simultaneously, then the fast acting devices will be doing all the reactive power. It will provide the reactive power requirement, and slow will not be able to do that. So once the fast finishes its work, the slow will start. So they will do independently all these things. So that is why they give importance to speed of operation of devices. The fast will act first, and then the slow will act. And this new scheme which has been proposed is, so in this case what will happen? The utilization of fast will be more. The fast devices will be used more at a more frequency, higher frequency. They will be utilized much more than the slower ones. So that utilization ratio is not good. So they want to make it balanced. Slow should also provide, fast should also. Both of them should be able to provide similar type of reactive power requirement. So for that we have to create a delay for the fast one. Suppose the problem here is fast is acting as soon as it receives a command. But slow, because of inherent delay, it is operating after some time. This is fast and this is slow. So this is the gap which we want to reduce. So what can be done here? How can we reduce this gap? Slow cannot be made fast, right? So what can be done?
Fast can be delayed.
So slow cannot be made fast. So what fast can be made slow, we can delay it. So we can reduce this gap by bringing fast here. Or even further based upon the requirement or the algorithm which is there. So that is why this scheme provides more effective utilization of devices by using this kind of delay mechanism. And it provides improved voltage profile and improved fault ride-through capability and improved transient condition of system. So first it will identify the operating condition of the grid, and then it will check for the availability of the devices, and then it will assign a master and slave role. So one of them will become master and other will follow slave. Let's say slow is made master and then fast will follow it. And then third, it introduces the time delay in the operation. This delay is introduced for the fast one, for the operation of fast. So by introducing this delay, we can ensure this both of them work simultaneously and share the reactive power requirement. Is this clear? Next one was this operation of parallel inverters. So this is fourth one, demonstration of parallel inverters operation in AC microgrid. Why do we need parallel inverter? Parallel operation of inverters, or in general generators.
Sharing of load.
Sharing of load is correct. Okay. What else?
Reliability will increase.
Yes, reliability will increase because they are connected parallel. We can bring one of them out for maintenance. And if you want to add new ones also, we can connect one more in parallel. Or capacity, we call it capacity enhancement or capacity upgradation. But then there are problems with parallel operation. Even parallel operation for of transformers also there is circulating currents, right? Here also these are two converters, two inverters or converters. First one is this, second one is this. Both are given two different references, and after the converter, before connecting it to the grid, there is one filter. So in previously L filter was used. Here LCL filter is used. Why do we use L filter? In even in buck boost or buck boost converters also we use L filter. Why do we use L filter?
To change the to stop the abrupt change of current.
Yes, that is correct. So because this inductor does not allow sudden change in current. So that principle is used. Correct. So we don't want that. So we want to, because output of DC should be like this. Ideally, it should be constant. But actual, if we see DC converter, it will be like this. So this is called ripple. The difference between these two, peak to peak ripple. So this we want to minimize, or we can say we call smoothing, for smoothing the current. Smoothing the current waveform, we add these filters. L filter, LCL filter, both are able to provide this smoothing of current. So it will reduce this ripple. It will be very small. So we have to design it carefully for reducing that. So it has its, you have to tune it. The frequency of the filter has to be designed based upon the our inverter. Required ripple that we want, current that we want to feed. So all that will decide the frequency and size, and that will also decide the size of these inductors. We can use L filter or LCL filter. Advantage of using LCL filter is that it is faster, attenuation rate is faster, it is more effective than L filter. That is why it is being used here. Then at PCC, both of them are connected. They are they are feeding these two current, I21 and I22. So these are so here there are two current components. One which is being fed into the grid by both of them, which is this I21 and I22, and one is in between these two. And there is a which is called as common current. One is common current, and another is this interactive current. So this one is responsible for feeding power into the grid, and this one is we call another name for that circulating current. It is flowing in between these two inverters, both the inverters, and it's a high frequency current. So if both the inverters are identical, then G11 and G22 are same, and G21 and G12 are same. So this is a matrix for transformation. So it's a transfer function matrix, we can say, because here we have control. This is a control system, so there is a gain. This is the output, and these two are inputs. It's a multi-input, multi-output system. There are two inputs and two outputs, so it's a two-input, two-output system. And the output is dependent on both the outputs are dependent on both the inputs. So here I21 is dependent upon both the pole voltages of both the inverters, VO1 and VO2. It depends upon both. Similarly, I22 also depends upon both. So this G11 and G22 are for this common current, this component which contribute to the common current, because they are feeding it into they are helping in the grid. So if G12 and G21 are not there, then it will be simply A21 will be G11 into VO1, and if and I22 will be only G22 into VO2. That is why they are only dependent on their own. And these two G12 and G21 are the components which these two are transfer function which relate one with the another voltage. So first one, the I21 is it becomes G11 into VO1 plus G12 into VO2. So it is dependent upon both the pole voltages. So if the second inverter is not there, then it will be simply this. Now because of interaction between the two inverters, one more component is here, which is because of the second inverter. Just like mutual inductances. Right? When we have two mutually coupled coils, then we will have this mutual inductance term. So if we talk about mutual inductance, then it will become L11, which is a self-inductance, and it will become I1, and it will be mutual inductance, or we call it M12, and it will become I2. So it is because of the interaction. One is self-term and one is because of that interaction. This is all these are calculations. After calculating, we get these two expression for GP and GC. GC they have defined it like this. GC has that term of this grid impedance also, LG. LG term is grid impedance is there in GC, but in GP it is not there. So it is defined like that. Similarly, these two resonant frequencies also, omega R and omega R1. Omega R1 is for here grid impedance is there, and omega R grid impedance is not there. One important thing to note is that common current and interactive current, they are proportional to, this is proportional to Iref1 minus Iref2, difference of the two reference current, and this is proportional to Iref1 plus Iref2. So if the reference current for both the inverter is same, what will happen to the interactive current?
Zero.
Yes, it will be, interactive current will be 0 if the reference for both the inverter is same. If it is not same, then it will be something. It will be difference between the two. So if the reference is same, then only the common current will be there, which will be, and the sum of the two will be fed into the grid.
So then always we have to do I reference 1 and I reference 2 to avoid this interactive current.
Yes, but it depends upon the requirement also. What is the requirement? How much current we want to feed from each of the inverter? So if we want to feed same current, then the reference will also be same. But if you want to feed different current, then the reference will not be same. So that will determine. If two inverters are exactly same, everything is same, then the reference will be same, exactly same. So this will happen in, suppose there is only in one wind farm or one solar panel, several inverters are connected in parallel because their rating is same, so their references are also same. In that case, inductive current will be zero. Two different inverters are connected, one solar farm, another solar farm. Their reference may not be same because it is dependent upon the rating of the inverter also. So that may be different. The last topic was the harmonic effects and mitigation strategy. Harmonic is a subset of, you can say, power quality issues. This is one type of power quality issue. Harmonic is one of the power quality issues. Harmonic is a subset of power quality issues. We have these two types of power quality issues. One is voltage related, second is current related. And voltage related, we have voltage sag, voltage swell, and voltage interruption. In current related, we have harmonics, notches, transients, and unbalanced load. Harmonics have several adverse impact on the power system. Even unbalance also has impact. So, can you tell what are the what are the adverse impact of unbalance in the system? What will happen if there is
Circulating current will move in the system, which will damage the system.
circulating current? How circulating current is even if there is unbalance, suppose there are three. Yes.
Ideally speaking, all the three phases should be same. But if there is no same, then neutral current will flow. That neutral current will damage the system.
Yeah, that is correct. So neutral current is there. It is if it is 4 wire. If there is a path for neutral current to flow, then neutral current will be there. That results in this oscillating neutral problem. It is correct. And another thing, so if there is path for neutral is not there, then also there is this oscillating neutral problem. And then the main problem for unbalanced load is this negative sequence component, negative sequence current. So their rotation is anti-clockwise, it's opposite to the.
A negative sequence will only happen when there is some fault.
No,
Otherwise,
even if there is because why negative sequence is there during fault? Because there is unbalance. Suppose there is LG fault. There is a fault from one phase to ground. So current in this fault is increased, but current in other two fault are not same. Means they are at normal values. That is why there is unbalance. Because in fault there is unbalance, and that will not always happen. Suppose there is triple LG fault, then there is no unbalance. So it will depend upon the type of the fault, and most of the fault they lead to unbalance. But even if there is no fault, if different loads are there, which is generally there in distribution system, loads are not same in all the three phases. Loads are distributed in the three phases, and they may not always be same. Even if we go in homes which are big homes or commercial, in industrial and commercial loads, their input is three phase supply, and they will distribute their loads onto these three phases. And it is not always that all the loads will be on simultaneously. Let's say home. At home, let's say one home has a, so let's say we have at our home we have 6 kVA installed. Our rated load is this much, 6 kVA, but entire load is not, and we have divided that our input supply is three phase, and we have divided the load. We have basement, ground, and first floor. So we have divided the loads. Even on each floor, the loads have been distributed in these three phases. Sometimes it happens that one of the phases is not available from the supply substation. Then in one room we have like the equipments are working, but in kitchen the refrigerator is not working. So it happens because the load is distributed in all the three phases. So, and it is not always that all the three phases the load is always same. So in that case there will be unbalance. And if unbalance is there, negative sequence currents are there, and which rotate opposite to the positive sequence currents. And because of that, they will create this, especially in these shaft of the motors. So they will try to rotate them in different directions, and that will create stress on this shaft. Especially these rotating devices, they have lot of problems. They have torsional strain, and that can damage their shaft, which also results into noise. So all these are problems because of this unbalance. Is this clear? So next thing is why, what are the sources for or causes of harmonics?
This negative sequence current will only give a stress, or that may also produce oscillation. Means it is giving a stress in the reverse direction of positive sequence. So oscillation is possible or only stress?
Yeah. So what will happen? Because negative, both are present, right? Positive sequence is also there, negative sequence is also there. So they will try to, one is trying to move in one direction, other is trying to rotate it in another direction. So because both are working, and it is not that always negative sequence is same. So unbalance is changing. So this stress is also having oscillation. That is correct. So the oscillation is not always constant. M down, it is possible. So why do we have harmonics? What are the causes?
Because the
Sorry, I could not hear. Can you repeat, please?
Inverter and converter action.
Yes, that is correct. So we have, these are the modern, we can say, modern sources of harmonics. So even before, when these converters were not present, were there another sources for harmonics? So there are some loads which are non-linear, like arc furnaces. Even these transformer itself is a non-linear device. What is the cause of non-linearity in transformer? Do you remember any cause of non-linearity in transformers?
because of hysteresis.
Yes, correct.
BH curve.
Yes, BH curve is non-linear, and because of that, we have, especially when we start the transformer, there is phenomena of this magnetic inrush. So there is a dominant third harmonic component in the current drawn from the supply. So all these things are causes of harmonics, and they can have several impacts like interaction with other power system equipments and motor and transformer. They can have additional heating and losses because the current is increasing, so it will create loss in the windings, and which will result into I square heating loss. Then there can be interference with the telecommunication lines, and there can be error in the control circuits. Control circuits are not designed; they are designed for fundamental, but because of harmonics, that is changing. So these are the representation of the different kinds of voltage power quality issues. First, these are voltage related issues. So here we can see this is the normal voltage, normal correct good voltage, and this is the sag where we have continuously there is reduction in the RMS voltage for few cycles. So there is guideline for that how many cycles, for how many cycles if it continues, it is called a voltage sag. I'm not remembering right now, but they, in IEEE they have the standard is there. So for particular number of cycles, if it continues, then it is called voltage sag. Similarly, voltage swell also it is temporary increase in the RMS value of the voltage. Here you can see there is increase in the voltage level. Then again after some time it will become normal. And this is interruption. There is voltage become zero for a few cycles. So there will be interruption of supply. And similarly for current also this is good normal current. Then here we have this is because of nonlinear loads. These are notches, high frequency transients. And notches can be because of these power electronic converters. And then these are unbalanced load. Three phases having different field loads. These are harmonics, and this is also single phase jump. So current in one phase becomes zero. It's a fault. So for mitigation of these harmonics, we have to use filters. We use filters. Different types of filters can be used. And this is around, I have to change this. Then there are two types of filters. One are passive filters, another are the active filters. So passive filters are our normal L and C filters. They are connected in. They can be connected in shunt, series, or hybrid. And they have been used for a long time. And they are still much in use in HVAC. High voltage AC, you would have heard of Ferranti effect. Have you heard of Ferranti effect? In Ferranti effect, this happens in these extra high voltage or high voltage lines when the load is less. Yes, when load is less or load is not there, receiving end voltage becomes more than the sending end voltage because of the charging line capacitance. Transmission line capacitance is providing more reactive power. and because it is providing more reactive power, we want, that's why it is boosting the receiving end voltage. So we want something, any component which can absorb that reactive power. So we connect a inductance, shunt reactor there to absorb the reactive power, and that brings down the voltage. So they are used because of their low cost, simplicity, and robust structure, and because of their reactive power compensation. So for this purpose, they are used in transmission system, and even for in distribution system, they are used for improving voltage profile. Because we see in the at the far end of the distribution system, the voltage reduces, voltage dips. So that to boost the voltage, we use even at the point for improve. So that is for improving the voltage profile. Then at the point of interconnection, power factor correction is used. So all the industrial consumers and commercial, they have to have a power factor correction, because so many loads are there which draw this harmonic current. So they need to install a capacitor bank which will provide that reactive power, so that the overall power drawn from the distribution grid is drawn at close to unity power factor. So if their load is drawing power at 0.75 lagging power factor, then they will install a capacitor so that they can bring it close to 1 PF, unity PF. Capacitor will provide that remaining reactive power. For reducing losses, for neutral current compensation, for load balancing, and better utilization of electrical equipments, all these are different uses for the distribution system. Even for one classic example is railway. So in railways, three phases have different. So three-phase supply is divided into three phases, and then because there are different platforms, so different phases have these different platforms. So they are divided. Or even other loads, the substation load or the platform, entire railway station load may be on one feeder. Another some train, different tracks are there. They are on another phases. So if train is not there on one track or even on 2-3 tracks, and it is there in some other track, then there is naturally imbalances there. To reduce that unbalance, also they do transposition. So after a few meters, they will interchange the ABC phases, so that unbalance is reduced. Even after that, if it is not reduced, then these passive elements are used. They will use these capacitor or shunt banks, these inductors and capacitors. So ideally, they can supply variable or fixed reactive power locally to compensate PQ or quality problems in the system, but they have certain limitations. Can you tell some limitations of these passive filters?
They are fixed.
Correct. So even if we provide number of steps, so those number of steps are fixed. If the system changes, some changes are there, they are not adaptable. They are not adaptable to varying system conditions due to their size and tuned frequency. So they are tuned to for a particular frequency, so that we cannot change once installed. So change in system frequency will detune the filter and it will cause increased distortion. And for effective filter design, the overall impedance must be less than the source impedance. So that is why a large size of filter is required, and which causes overcompensation. So that is their limitation, and that is why active filters are introduced, so that they can adapt, because they have these converters. They are based on converters, as we can see on this slide. So in active filter also we can have shunt, series, and third is hybrid, which is UPQC. which is Unified Power Controller. So shunt is used to mitigate current related problems. For example, D-STATCOM. So for distribution STATCOM, D for distribution. And for series, we have current series. We can use it for voltage related problems. So, for example, dynamic voltage restorer. And then UPQC can provide both type of shunt and series. And that is why you can use it for both voltage and current related problems. So these are the examples of the passive. So these two are shunt and these two are series.
Sir, how all these structures are helping in EV charging?
Actually, there is one case study which was considered. This was that experimental setup. And also, I think this this is not correct. I have to change this. Sorry for. Thank you for fighting out. I will change this. This is not for EV charging. Sorry. You are correct. I think it has been copied from the previous week's. Title has been copied. Nothing to do with this EV charging center. Even in EV charging infrastructure, it can happen. We require filter will be required, but this is discussion. Today's discussion is not related to that. Sorry for that.
Yes, sir. Yes. Nice.
So yes, DVR dynamic voltage restorer, D-STATCOM and UPQC. So this is the example of that case study was example of that UPQC. So here we can see this is one active filter and this is second active filter. So this is acting as this is series active filter and this is shunt active filter. So this series active filter will be used for current related or voltage related. Just now we discussed.
What was question, sir?
So there are two converters, right? We have one is acting as series active filter and second one is acting as the shunt active filter. So which one will be used for correcting voltage related problems and which one will be used for correcting current related problems?
Name is suggesting, sir, series, but both may be used in voltage correcting issue, series shunt. No, series will be used to check the current.
We discussed
And shunt.
we discussed that Faraday effect. Voltage was increasing, so we were using that
Yes.
shunt reactor, right? So shunt we are using for voltages. Here we can see, right?
Yes, sir, shunt will be used for voltage.
This is active, series active filter, which is dynamic voltage restorer. So series we are using for voltage related problems. And shunt we are using for current related problems. Here it is drawing current. So here series is using for voltage, shunt is using for current related problems. Okay. So here
Yes.
this the grid side converter is acting as the series active filter, and which is connected to this series injection transformer. First one. So it will behave as a pure sinusoidal current source because it is connected in series and offers a high impedance path for the load harmonics because it is connected in series. So because it will provide a high impedance path, so the harmonics will not flow, right? And the LC filter which is connected in series, it is used to reduce the switching harmonics produced by the converter. Then the shunt one, second one, which is connected on the load side, it behaves as a pure sinusoidal voltage source. And thus because it is connected in shunt, so it will provide the low impedance path for the harmonics. So because it is providing low impedance path, so harmonics will flow through that and it will not flow to the grid side. Correct? Is this clear?
Yes, sir.
So both ways they are blocking. One is creating in between here high impedance so that it will not draw harmonics. And this is providing low impedance, so harmonics will flow this side, not to this side, not injected into the grid or not drawn. Whatever harmonic required will come through this side. This will provide it in one sense to the this nonlinear load. Let us take questions now. Please copy to all the slides. I'm not able to remove this. What's happening? Sorry for that. I don't know what is happening. I'm able to remove this.
No issues, sir. Question was visual.
Okay, so first question is this. Sorry for this. The purpose of microgrid modeling and simulation is first one, conducting rigorous analysis, identify key challenges, feasible solution before physical implementation. Which one is or are correct?
C option, sir.
Why not A and B?
Because, sir, all of the above option is not there.
Yeah, so
Otherwise,
we can
key
choose
challenge.
multiple choices there. We can select.
Then A, B, C, sir. All.
Yes, correct. So today I think multiple choices are there. We can select more than one option. Next one is this: identify the incorrect statement with regards to inverter control of PV and ESS in microgrid. So first option is PV and storage controls are based on decoupled EQ control strategy. Second is PV and battery storage are interfaced to AC using dynamic average model of their DC-AC voltage source. Dynamic average model represent high switching frequency dynamics and they allow higher switching simulation time step for modeling larger microgrid cases. This thing we didn't discuss, but if you remember something from lecture, can you answer based upon that? Otherwise, I will explain that. What do you think? Which one is correct? This we have seen, right? PQ control strategy. all the control which we are studying are decoupled because of this transformation, the DQ frame transformation. That is one advantage of this DQ transformation. When we convert this ABC into DQ, then this PQ equations, they become decoupled. So P is dependent on ID, Q is dependent on IQ. Not P is not dependent on both of them. This we are able to achieve. That is why first is correct. Then these models are their model using dynamic average model because we can have steady state. We can study steady state behavior and transient behavior of the converter. For studying the transient behavior, transient means there will be microsecond. Means we want to see what is happening at millisecond and microsecond level. So if you want to see at such small time steps, then our simulation has to work at that small time step, millisecond, microsecond. If you want to simulate that, then it will take time. Integration and all that thing has to be done at each millisecond, each microsecond. So that is computationally very intensive. So to avoid
in this, what is the answer?
Answer will be the C is not correct. D is correct and A, B, D.
D, sir.
So A, B and D. This is the answer. Oh, sorry. Incorrect was asked. So C is the answer. C is incorrect here. Because dynamic average model are used to study only the steady state behavior. We are not. So this model will not give us transient switching frequency. High frequency component we cannot see. So based upon what we want to see, we have to choose models. If we are only interested in steady state performance, not on the dynamic performance, then we can use these average models and we can run the simulation quickly. We can use large time step, maybe few seconds, and we can still get the output. But if we are interested in understanding the dynamic behavior, what is happening at each millisecond, each nanosecond, each microsecond, then the simulation time step has to be smaller than that our time of interest. If I want to see what is happening at each 1 nanosecond, the time step has to be at least 1 nanosecond or less than that. And that will make computation at each nanosecond, the solver has to solve it. It will become very computationally intensive. So that is why for average models, we can use larger time step and run our simulations very quickly. And if you want to study both, then also we have to use that small time step. If you want to capture everything, steady state as well, dynamic as well, then also we have to. So whatever simulation we are doing, we have to choose time step such that the smallest or the largest frequency component corresponding to that we have to take the time step. So time step will be inverse of that largest frequency component. So it will be much smaller if frequency component is quite large. So if you want to see high switching transients, very high frequency components, then we have to choose a very small time step, and that will be very computationally intensive. So if we are only interested in fundamental frequency component, we can use dynamic average model. Is this clear? Next question is function of diesel generator in the AC microgrid is R. First is frequency regulation by changing mechanical input. Second is terminal voltage regulation by varying field current through excitation, and third, normally excited synchronous generator operated 0.8 power factor.
Option D, sir.
Option D.
D. terminal voltage regulation by varying field current through excitation.
Why not A?
It is all is the answer.
Normally excited synchronous project, 0.8 power factor,
All of the above is not correct. There is
frequency regulation by changing
because this option. Check this option carefully. C option.
normally excited
There are three conditions: under-excited, over-excited, and normally excited. So normally excited, what will happen? Leading, lagging, or UPF.
UPS
This normally excited means UPF. So this is not correct. C option is not correct.
option AV. Yes, sir.
Again, there. Next is which statement is are correct with regards to inter DC power flow. So this is for when two microgrids are connected, interconnected. So first is isolation is not provided. Effective control and coordination is achieved without communication. High control